Suppose we take our circuit of a battery and a light bulb, and we make it slightly more complicated by adding a switch. When the switch opens, the charged particles are prevented from passing through. Particles with the same charge repel one another, and they therefore spread out throughout the wire. The events shown here all happen at the same time, and this is the result. For the light bulb to turn on, the switch must close, so as to create a complete path for the charged particles to flow around the loop. If we have several light bulbs, each light bulb can have its own individual switch. Or we can have one switch which controls all the light bulbs. The number of charged particles that pass by each second is what we refer to as the current. The charged particles flow through the light bulb because the battery causes them to have a higher potential energy on one side of the light bulb than the other. This potential energy is what we refer to as voltage. If both sides of a light bulb are at the same voltage, then no current will pass through it. As the voltage across the light bulb increases, the amount of current through the light bulb also increases, and the light bulb produces more light. When a switch closes, it causes the two different parts of a circuit that it connects to be at the same potential energy. If both sides of a light bulb are at the same voltage, then no current will pass through it. And if no current passes through a light bulb, then this means that both sides of the bulb are at the same voltage. A properly working battery ensures that the difference in voltage across it is always at a specific value. All points that are directly connected to each other through metal conductors and closed switches are at the same voltage. This means that if we have several light bulbs connected to a battery in parallel, the voltage across each light bulb is equal to the voltage that is produced by the battery. Since the voltage across the light bulb determines how much current passes through it, each of these light bulbs will have the same current pass through it as we had when we had just one light bulb connected to the battery. The total current drawn from the battery is the sum of all the currents drawn by each of the light bulbs. Now, let us consider a situation where we have several light bulbs connected in series. Since the total voltage across the group of light bulbs is at the specific value set by the battery, the drop in voltage across each light bulb is only a fraction of this. Since the current that passes through each light bulb depends on the voltage across it, this smaller voltage across each of the light bulbs means that a smaller current will flow through them. This means that the lights will not be as bright. Because the light bulbs are connected in series, this means that the current passing through each of them is the same. The amount of current entering always has to be equal to the amount of current exiting. This is what we refer to as Kirchhoff's current law. This is accompanied by another law called Kirchhoff's voltage law, which states that as we travel around a loop, the amount of voltage increases that we experience must be exactly equal to the amount of voltage drops that we experience. The use of these two laws together allows us to analyze all electric circuits, no matter how complex they become.